Well, good afternoon, everybody, and welcome to the second of today's webinars from Smart Vision Europe. In this second webinar, we're looking at regression techniques, again, focusing, as we did in the previous webinar, on healthcare applications. My name's Jarlath Quinn. I'm joined online today by my colleague Rachel, who will be making sure that everybody's correctly uh, checked in and is managing to access everything appropriately. If you haven't joined any of these sessions before, you should be aware that we do record them, so you'll be able to listen to them again afterwards. And we do provide a copy of the slides. We'll email out a link to you to download any materials that we show after the session's ended. If you think it's particularly relevant for colleagues who are unable to join us today, and you can get enough of them together, the chances are that we can probably rearrange it or rerun it on a private basis. The best thing to do is just to send us an email and we'll see if we can do that. And with regard to asking questions, all the lines are muted. So we ask you to use the chat panel. And if we run out of time, we will try to follow up with you offline afterwards. But you can, of course, just drop us an email. When we usually get a couple of emails after each of these sessions from people who, once they've had time to digest and think about, the stuff they're showing here, might be able to send us an email afterwards, and we'll take our time to answer it thoroughly. If you don't know who we are a technology company. We're a gold accredited partner to IBM, as well as a company called Predictive Solutions and Data Robot, and we specialize in statistics, advanced analytics, data science, machine learning technologies. And we also work with open source technologies such as R and Python and Spark. We're a relatively small organization, but as a team, we've got very deep history, 15 to 35 years working in the advanced predictive analytics industry, including SPSS, SAS, IBM, companies like that. And that means we've got very deep experience of applying advanced analytics applications across many different sectors, healthcare being one of them. And certainly things like using linear regression and logistic regression, which we're going to talk about today in healthcare applications, is something that we're very, very used to and are familiar with. So our agenda today is to start off gently at trying to introduce the concept of regression by starting talking about correlations, which is a nice way to introduce regression correlations being an interesting and useful technique and approach in and of themselves. In fact, we run a webinar specifically for correlations. So if you're interested in that, there'll be a recording of that on YouTube and also on our website. Then we'll walk up to simple linear regression before we get into multiple linear regression to model per capita cancer mortality rates. And we can also identify problems in linear regression models. So we can talk about, how we do that, introducing logistic regression and working with logistic regression to model low birth weight. So what do we mean by regression? Well, one of the things that can that tends to get overlooked with regression is, in fact, it's a family of techniques. It's not a single technique. You do hear people saying, "I just used regression." Well, that could mean different things. Linear regression is used when the outcome is continuous in nature or scale data, so it's a numerical data, and also when the relationship between the fields can be described using straight lines. So when they're linear relationships, meaning straight lines, logistic regression is used when the outcome is a category or a class of some sort. Binary logistic regression refers to a two-category outcome, and multinomial logistic regression refers to when you have a three-category outcome. And then you have variants of that. You have things like quadratic regression, which is a variant linear regression where the outcome is continuous, but the relationship is very much curvy linear in nature. It might be something that's used with growth, so it could be used with outbreak of an illness or something like that, or a particular disease, because it tends to be used to model growth curves. And then you have Poisson regression, which is modeling count data. So count data being the frequency of occurrence of something that occurs, often things which occur relatively rarely, or where people, tend not to have very high values for them, such as, the number of times they've been admitted to hospital. And also used to measure, never events, times when things occur very rarely, such as fatalities during, surgery or something like that. But which nevertheless do features as as an aspect of the background population. So Poisson regression is another type. We have a video on Poisson regression. So if you're working with count data, you might want to check out that video on that as well. That'll be on YouTube and on our website. So let's talk about linear regression in healthcare before we start talking about correlations per se. So linear regression is used when we want to model, for example, the relationship between things like blood pressure and diet. It could be salt intake and blood pressure. Or if we wanted to estimate treatment costs based on, patient comorbidity, something like that. You might want to predict visual acuity based on treatment and age-related factors. You might be estimating some sort of level. It could be a calcium level, or it could be a cholesterol level, or something like that, based on lifestyle or based upon demographic factors, or predicting recovery time based on demographic and severity of treatment factors. So there are lots and lots of different applications where one might be employing linear regression, both within a sort of research capacity and also within a sort of administrative or treatment capacity. Um, the term regression is actually a shortened term. It's actually shortened for regression to the mean, which means falling back towards the average. So it just means regression to the mean, falling back towards the average. Here we have a little scatter plot. It's usually used to illustrate regressive techniques, a scatter plot. And here we have on the vertical axis, we have the percent reliant on public healthcare and percent unemployed. And each one of these little points or dots represents a US county. So they're geographical regions. And we simply measured within each county, what proportion of people are completely reliant on public healthcare. They don't have their own private healthcare. And what percentage are unemployed in that county. And of course, what we find is that there is a relationship between the two. It's an obvious relationship. You can see here, it's a positive linear relationship. And if we wanted to kind of simplify that, we could take the mean of one of these variables. You can say, what's the mean percent reliant on public healthcare? What's the average, if you like? And if we do that, you can see that it really tries to fall back towards it, effectively being described as a straight line. It's as if it's trying to linearize itself into a straight line. This is exactly what we mean by regression to the mean, that things fall back towards an average, and we try to simplify the relationships in terms of talking about the average of it. So the idea that that there is an underlying linear expression which can be where the values effectively fall back as if they're gravitationally pulled towards the average, the overall underlying average or the mean relationship. So that means that you could put a straight line through a relationship like the one that we're looking at here. And that straight line would represent effectively the mean of that relationship. It's the line of it's the line of least squares as it's called, and we'll talk about that in a little bit more. But when we're building a regression model, and we're pulling out numbers that show us how to predict, for example, the percentage of people who are reliant on public health care based on percent employed. What we're really doing is we're describing that line, and we're coming up with a formula for that line, as we'll see. So this line, this regression line, is drawn in such a way that it minimizes the differences between each of the points in the line itself. So it's called the line of least squares. It's called the line of least squares because if we added up all the differences between the points in the line itself, some of the points would be under the line, so they'd have a negative value. Some of them would be above the line, they'd have positive values, and if we added them all up, they just sum to zero because the positives and the negatives would cancel each other out. So what we tend to do is we tend to square the differences to get rid of that negativity value. So -3 squared would be 9, +2 squared would be 4, of course. We could add them all up, and what we're trying to do is come up with the smallest number. So we're fitting the line in such a way that that number is as small as possible, and that line is then referred to as the line of least squares, of the smallest squared sum. But the thing about it is that's just a straight line. I mean, it doesn't really necessarily describe the relationship that you're seeing, that you're visualizing, and that's why visualizing is so important in adding, doing things like scatter plots. And this is a famous graphic called Anscombe's quartet. It shows exactly the same line, in other words, the same regression model, if you like, but the data is very different. So you got the first one here, which is kind of your typical example of a regression model. The second one, we have a curve, we have a curved linear relationship. Straight line will just pass through that. It can't see the curve, it can't fit itself to a curve, so it may not describe it well. The line is affected by extreme values. If you've got a relatively small number of cases, you've got one extreme value. Because the line is effectively an average, it's a bit like taking an average of people in the room and somebody walks in who's, 7 foot tall and the average goes up. So we do have to be aware that extreme values can affect the model, can affect the line of these squares, because after all, it's trying to take an average. And there are even situations where, you could just have two values. Here we have a value of 8 and a number of cases of a value of 8 and one case of a value of 20 or 19 or something like that. It still draws exactly the same relationship because it's trying to create this. It's effectively just an average after all. So we do need to bear that in mind. We do need to explore our data, and we do need to, think about the fact that if the data is and doesn't, a straight line isn't going to describe it very well, the various options we might take to deal with that. We might use a different technique. We might use a non-linear technique, or we might try to straighten the relationships by doing things like taking logs of values or taking the square root of values, which often tends to straighten out relationships. Okay. Talking about measuring linear relationships and trying to find out how strong relationships exist between different factors, we might use something like a correlation to do that. And the correlation, again, we're looking at scatter plots here, is effectively a number that ranges from -1 to +1. It can't go beyond that point of 0 in the middle. Here, each of the points isn't a patient, but it's in fact an automobile. And so each one of these points is an automobile. It's not a region or a patient. And, it's we're looking at factors where two variables are correlated, the horsepower and the vehicle weight. Well, the vehicle weight is related to the horsepower because the cars tend to be heavier if they've got a big engine in them. If they've got a big engine, then they tend to have more horsepower, and thus we can express this as a scatter plot, and we can see that there's a strong relationship that as one value ascends, the other value tends to go up as well. And as a correlation, because that's quite close to one, it's not perfect correlation, it's 0.859, that's strong linear correlation. A weaker correlation is the relationship between time to accelerate from 0 to 60 and miles per gallon. It's still a linear relationship, but it's weaker, and we can see it's a bit more fuzzy. If we put a line through here, it wouldn't fit the data as well, and thus the correlation is weaker at 0.434. And you can have negative correlation, so you could have something like the relationship between, um, yeah, I think the example I always use is alcohol intake and reflex reaction time. These are negatively correlated, so people's reflexes tend to be worse when they imbibe a lot of alcohol. And thus you get negative relationships. You can get things like that with blood pressure and certain drugs and stuff like that, where as one dosage increases, another value goes down, and thus and so forth. Again, this is a relatively strong correlation here. Looks like a good scatter plot, but it's going in the opposite direction, so it's a minus correlation, but still a strong correlation. Correlations where the data is very close to 0, where there's really no relationship between the vectors, such as here, miles per gallon against mileage, they're going to be effectively there's going to be no examples on linearity, and if you were to put a line through it, it would just come out quite flat. It wouldn't describe the data very well. That would indicate that the correlation was probably didn't exist, and but therefore would be close to 0. And of course, you can still get relatively strong correlations, as we've already pointed out in the Anscombe's quartet graphic that we showed earlier on. even when the relationship is not uh, linear in nature, even when it's curvy linear, it doesn't see that. You can still get a strong linear relationship, but ideally, you're losing something if you're not modeling the data. You'll notice that here, in order to create this chart, I have taken miles per gallon and I've squared it. So by the same reasoning, if I take the square root of this, it will actually straighten out the relationship. So hence, sometimes transforming the data is a useful way to try and straighten or linearize the relationship between variables. Um, I'm going to do some correlations in a moment, but I just wanted to point out something to you that a correlation which always runs from -1 to +1, you should bear in mind that this correlation value can be squared itself. So if you take a correlation of, minus zero point 0.3, and you square that, minus zero point 0.3 is not a very strong correlation. But if you square it, it comes out as point 0.09. Of course, the minus numbers cancel each other out. You're just multiplying it by itself. And that becomes what's called an R square. And it can be expressed as a percentage. So here we have horsepower against vehicle weight, and the correlation is 0.859. If we square that correlation number, it comes out as 0.738. And that is 73.8% variance or variation. That's what it refers to. It's called the R square. And it really refers to, excuse me, the percentage overlap between one variable and another. It's saying how much variation in one variable can be used to explain another. So you could almost think of this as two circles overlapping in a Venn diagram, and they overlap by 73%. So it means that one variable is a very good predictor of the other because it can account for 73% of the variation. And the R square is important because that's one of the things that we use to measure how well the model fits the data. In fact, it's a key statistic, an R square value. It's just the square of a correlation. If you think about it and work the logic on it, zero point 0.3 squared, 0.09, 9%. Zero point 0.4 squared, 0.16, 16%. Zero point 0.5 squared comes out as 0.25, 25%. Zero point 0.6, 36%, correlation of zero point 0.7, 49%. So you need to get to a correlation of zero point 0.7 before you're explaining almost half of the variation in one variable using another, or in one variable using a group of other variables, which is what we do with multilinear correlation, where we use a group of variables and they all contribute towards the R square, which we'll see in a moment. Let's just jump out to some data before we get to this. Do a wee bit of correlation before we do any further analysis. So I'm just going to go out. I've got some data here. This is the data I was referring to earlier on, which is cancer mortality rates. And I'm just going to do some quick correlations here. Each of these records represents a different US county. So it's all sociodemographic information, the economic information. And if I looked at something like, let's just do some basic correlations. I'll go down to correlate here to bivariate, and I'll pick something like mean per capita cancer mortalities, so average per capita cancer mortalities, against percentage of populace in poverty. Okay, so what's the relationship between poverty and cancer? And I'm going to just change some of the display here because you generally only want to show the lower triangle of the matrix that it creates and not show the diagonal because that just shows the variable correlated against itself. Just get into the habit of clicking those two boxes. And it says the correlation here is 0.429, which is a positive correlation. It's a statistically significant correlation. Significance isn't that important here because it's just testing whether or not the correlation is zero. Well, it's not zero. That doesn't mean it's strong correlation. And it's based on 3,047 cases, but it's 0.429. If we were to square that, it would be somewhere between 16% or an R square of 0.16 and I guess 0.2, something like that. I don't know, say 20%, somewhere between 16% and 20%, something like that. And that's the level of overlap between percent of population in poverty and mean per capita cancer mortalities. If I throw in some other variables in here, I could throw in like the population of the county. Would that actually relate to that? What about the median age of men within the county? And let's pick another interesting, let's say a percentage of married households. We throw that in. Click OK. Now we're going to get a whole matrix of correlations. And you can see a lot of them are negative. So it's saying that basically, but they're quite weak though, not very, very weak here. This one here, median age of male county residents, is negatively correlated with mean per capita cancer mortalities, but it's not statistically significant. It's so close to zero that it's saying I can't guarantee that's not zero. The rest are quite weak. This is quite strong though. Percent of married households against percent of population poverty. That's minus zero point 0.6, indicating that the higher the percentage of married households, the smaller the the lower the percentage of the population in poverty. And here we have percent of married households against median age. This is actually it's a significant correlation. It's quite a weak correlation, 0.202. If it was just zero point 0.2, then we squared that, it'd be 0.04. It would only be 4% of the variation in one variable matches the other. Whereas here's minus zero point 0.6. That's a 36% overlap between these two variables. So the fact that it's a negative correlation makes no difference. It doesn't mean anything. It just tells us the direction of the relationship. So correlations are a way for us to measure this, almost to illustrate a scatter plot in terms of its linearity in a single value, and obviously they're going to be very important to regression, in the sense that regression looks at the relationship between linear variables, and by squaring the correlation value, we can tell what percentage of the variation in one variable is accounted for using the other, or what the percentage overlap is, and what the explainability is of it. So that's useful. What about actually turning these relationships into predictive models? How do we do that? Well, we got to return to that straight line that we talked about earlier on. And the best way to start thinking about that is just ask yourself, how long does it take to cook a chicken? This is an easy way to remember this. How long does it take to cook a chicken? Well, depending on who you're asking and depending on the temperature of the oven and stuff like that and other factors, you might, if you ask Julia Child, she'll say 7 minutes per pound plus 45 minutes for good measure. You ask Delia Smith, it'll be 20 minutes per pound plus 20 minutes for good measure. So if Delia Smith says that if you've got a 5 pound chicken, then that's going to be effectively 120 minutes to cook it. Quite a long time, but then we don't know what temperature she's cooking it at for a 5 pound chicken. But that's how we work that out. And the point is that this is a linear regression equation. It's a linear regression equation. Both of these are linear regression equations. They have both the same form. They're the equation for the straight line. That's basically, we taught this in school. And depending whether or not you're a mathematician or a statistician, you might express that as y, meaning how long it takes. That's what the y is, the time variable. Mx plus c. Well, the plus c is the plus 20, 45 minutes, or here it's a, it's plus 20 minutes. This is kind of a statistical approach to it, where a is basically the constant. You're basically saying no matter how much the chicken weighs, you're always going to add on 20 minutes. And B is the 20 minutes per pound. That's called the coefficient. X is the actual weight of the chicken. So B times X. So when we run our linear regression, it's going to give us an A and it's going to give us a B. And those are the two numbers it's going to give us. It's going to say, I'm going to tell you the 20 minutes per, and I'm going to tell you the plus 20 minutes on the end, whatever those numbers are, in order to predict the outcome that you're trying to predict, such as blood pressure or cholesterol level or, recovery time or whatever it is that you're trying to predict. So when I do a scatter plot here of percent reliant on public health care and percent unemployed, I can actually ask it to put in a straight line. And when SPSS does that, it gives me the formula. It tells me the formula here. It's y equals mx plus c, or y equals a plus bx. Here's a plus bx. Here's the a. That's the constant. It says you've got to start if you're trying to predict y. Y is the vertical axis. Then you start with 10%. Basically, it says sorry. You start with 10% down here. It says public health care, because not very many are below 10%. And you should add on 1.16 for every value of X. So it's saying that if you took 10% unemployed and you multiplied that by 1.16, it's obviously going to be 11.6%. And then you add on what 10.13 onto that. So it's going to come out as about 21 point, 79%, something like that. So it's going to come out around about here. So 21.7. That's where that line intersects, basically. So that's it. That's just simple linear regression. So we can use linear regression here to model regional per capita cancer rates. Let's do that. Let's go and get it to give us these values. Just to show you once again, if I just do a quick chart and just do a quick scatter plot so you can see how to visualize these relationships. This is my mean per capita cancer rates. So I'm putting that on y-axis, and then I can take something like I'll just display the variable names. I'll say something. I'll find something like percent in poverty. There you go, poverty percent along the bottom here. Click OK. It's producing this chart for me, as we saw earlier, and I could ask it to put a fit line in, to put a linear regression fit line in, which is what it does, and it's giving me here, because it's percent of populace in poverty, it's giving me a little regression equation out the back of that. And if I wanted to edit this, I could do so, of course. I could change the colors and the sizes of these points, etc., etc. Yeah. So there you go. Okay, so this is what we're modeling. So, all right, before I go any further, I should just point out in SPSS you can hide variables. This is quite a lot of data, a lot of variables in here. It's quite confusing. So I'm just going to hide some of them using a variable set. Just going to click that off, and that just gives me a smaller number of variables. And if I go now to build a linear regression model, I'll go to analyze down to regression, down to well, you can see there's a lot of different regression techniques in SPSS. There's loads of them there. So the one we normally go for is linear, but you can see there's tons of other types of regression techniques, hence it being a family of techniques. I go for linear. I need to pick out what my dependent variable is. That's the target thing, the thing I'm trying to predict. Well, this is the thing I'm trying to predict, which is mean per capita cancer mortalities. And if I pick something like median income per county, let's just pick that, let's say to begin with. We'll click OK. This will help us familiarize ourselves with the output that the linear regression produces. So I click OK at that point. It runs the linear regression. I'm just going to close these other bits of output here so you can't see them. So we can just focus on linear regression. You can see it saying, okay, this is the variable that's been entered, median income per county. The method is called enter. That means forced entry. You're just forcing it in whether it's any good or not. We can see that the R value, that's the correlation, is 0.429. And when we square that, that comes out as 0.184. And what we normally quote, though, is something called the adjusted R square. The adjusted R square is just an adjustment for the variability, the sample size, and for the complexity of the model. And it's always a little bit lower than the R square. So this is what we really, it's kind of more realistic estimate. And this adjusted R score comes out as effectively 183. It means 18.3% of the variation in the mean mortality can be accounted for if you know the median income for each county. So for a given county, on average, you could account for 18% of the variation. You'd be within 18% of the true number. The next thing we see is an ANOVA table. And if this seems unusual to see an ANOVA table in here, you should bear in mind that most statistical packages, whether they be SPSS or SAS or Stata or S plus or even R to a certain extent, they tend to show the same output for R, and they often show a model summary at the start telling you how well the model's fitting, giving you an adjusted R square, and then they give you an ANOVA table. And the ANOVA table is really there just to say, is this any better than doing an average, just taking the average value of that? If I wanted the average value, I could say, okay, what's the average value for this variable, this death rate variable? Well, the average is 178 per 100,000. That's what the average cancer mortality rate is. I mean, you could just say, well, I'm just going to assume everybody's the average, and that would get you so far. And what the test here is doing, it's saying, is that significantly better And just assuming that you take the average of that. And it's saying, yes, it is, because if the value is 0.000 or less than 0.05, you're rejecting the null hypothesis that it's no better than taking an average. So you'd kind of expect this ANOVA table to always be significant, to be statistically significant. If your R square is, in any shape or form, reasonably strong. And here it's quite weak. I mean, we only got one variable and it's only 18%, but still, if we're trying to model the relationship between one factor and another, that could be almost immaterial. We want to see what impact income has on on uh, the cancer rate. Then we're going to look at the last table down here, which is the coefficient table. And the coefficient table gives us our two values, our y equals mx plus c, our 20 minutes per pound plus 20 minutes per good measure. And the first thing is it gives us a constant. The constant it says basically is your minimum value. It says, well, I'm going to assume you have a value of 225 people per 100,000. That's what your cancer mortality rate is. And that is statistically significant. It's actually saying, yeah, it's helping in the model. It makes a difference to the model. And then we get median income per county. And instead of getting like a big number, we get a really, really tiny number. We get this tiny, tiny number. Look at this. So I just double click on it. It's actually 0.00098. That means for every increase in income, every $1 increase in income, you get a decrease in the death rate of 0.001, which is really tiny. Why is that happening? Well, let's look at the median income. Median income is literally measured down into individual dollars. So it's talking about the difference between 61,898 and 61,899. So it's kind of hard to interpret that. So one of the things I could do is I could just say, well, look, let's just turn it into thousands or something like that. So I'll call it med. I'm going to create a new variable here, med income, and just underscore thousands. I'll just give it a little label, median income in thousands. Yeah. And of course, all I'm going to do then is take median income and basically divide it by 1,000. That's what I'm going to do. So I've got a new version of this variable. Click OK. And then I rerun my linear regression using the new variable, which is now at the end there, median income in thousands. Click OK. And of course, because the units affect the coefficient, we're now saying, look, now saying for every 1,000 increase in median income, which is this variable's over here. Look, here it is over here. Look, it's 61,000.9. So every 1,000 increase in median income, it's much easier to interpret now. Uh, you're getting a drop of about 0.988, so it's nearly one person. So basically, for every 1,000 increase in median income for that county, you get one fewer deaths in the cancer mortality rate. Yeah, and you could do the same thing with by splitting it into deciles. And some of the earlier examples of this, I've split it into deciles and shown how to do that. But I'm not going to labor that at this point in time. All we've done now is we've said, okay, that's the effect of that upon that variable, and we can see that the adjusted R score is 18.3%. What happens if I add in another variable? What happens if I go back to it and say, well, let's look at percent of population in poverty? Well, these two things are obviously going to be related to each other because obviously if your income's higher, population's lower. We need to be careful about that because when you start to add in variables which are highly correlated with each other, are you not just measuring the same thing? If you might put in, you wouldn't put in weight and height and BMI because they're ultimately the same thing. So that can mess up your model. You want the variables to be sufficiently independent of one another. We click OK at this point, however, and we run it now. You can see that the adjusted R square has jumped to 0.2. So now it's 20%. Of course, the ANOVA table is still significant. And now we have two factors. Now, the two factors are saying median income now drops by 0.5. So you get for every 1 unit increase in median income, you get half a person, one fewer deaths. But for every percent increase, for every 1% increase in population in poverty, you get one more death. So one of these is negative, one of these is positive, of course. Now let's just compare and contrast that to the previous coefficient table where we only had one value in it. Look at this number here, this beta coefficient, this beta value. This is a standardized, that means a standardized version of that number there. It's standardized because that's in the original units of the dependent variable. But sorry, this is the original unit standard dependent variable. When we standardize it, we kind of turn it into a correlation. So it will run from -1 to +1. So it's been standardized. And it's actually in this case, it's exactly the same as the R value. Look at that. It's exactly the same. Mine here, it's just showing me the direction. -4.29, because that's what it is. It's the correlation. But because it's the only variable in there, it's the only variable being used, the correlation is exactly the same as the R value. So same as the correlation between median income and the dependent variable. But now we've put two variables in, and the correlation can't be the same because they have to account for each other. So these become what are called partial correlations. They show how much of this variable is correlating with the dependent variable, which is cancer mortality, in the presence of in the presence of this variable here, percent populace in poverty. In other words, it's controlling for it. That's what we're saying. So if you wanted to control for it, if you said, "Oh, I know what's really driving this. What's really driving this relationship is its age. It's actually the average age in there. It's like that's related to income." And that's what's really driving. If you put age in, you would effectively be controlling for age, and you would suddenly see that correlation disappear, and it would become very, very weak. Because if you were right, then the age variable would show that there actually wasn't much more relationship between median income, and it was all driven by age. But here they're both contributing towards it. They've both got fairly weak correlations, but these are quite good partial correlations, and they're showing the relative impact of each variable to the other. So that's interesting. So now if I add in another variable, let's add in another one. Let's go in. Let's say these people with bachelor's degree. We'll put that in. I'll pull that in. Let's see what happens now. Okay, now I'm just going to make this table cell a bit wider so you can read it out. So you can read it a bit more clearly. But now you can see it's like saying median income in thousands is now really quite weak. It's really quite weak. The partial correlation values. Look at that. It's no longer statistically significant. It's no longer statistically significant because we put in this variable percent of county residents aged 25 and over where their highest education is bachelor's degree. In other words, this variable measures the percentage of people in that county who are graduates. And that is more dominant than median income. So median income no longer is really an important factor. And in fact, it says, for every 1% increase in the graduate rate, you have nearly two less deaths from cancer in that county. So very interesting. So what happens if we want to throw them all in? If we threw them all in, of course, this is called forced entry. I wouldn't put in mean number of reported cancer diagnosed annually because that's obviously going to be that's cheating. That's going to be too related to that. If I threw them all in, you're going to end up with quite a messy model as you put them all in here. This is called forced entry. We're just forcing them all in. Some of them are significant, some of them aren't significant. So another approach is to say I'm going to change the method from enter to forward. If I change it to forward, then it puts them in one at a time in terms of their importance. And it'll actually build multiple models and stack them on top of each other. So it's called forward entry. It's built 5 models here. The first one that's put in is the graduate rate. Next one that's put in is the marriage percent. Third one that's put in is employment percentage for adults. Fourth one that's put in is median income per county. And the fifth one that's put in is percent of population in poverty. Let's have a look at that. So now it said, okay, look, the adjusted R score has gone from 0.233 to 0.298, so nearly 30%. The ANOVA tables for each step in the model, as we built 5 models, are all significant. And here are the coefficient tables. And if I just expand this out to make it a wee bit more readable, you can see that in the first model, there's percent of county residents going in. There's the coefficient, there's the beta value, there's the partial correlation. Then percent of county residents, that's graduate rate and married. So now it's having to deal with that. It's got a little bit weaker. And this is percent of married households and county residents aged over 16. So that's a percentage of county residents aged over 16 in employment. So the employment variable goes in quite weak. Everything's statistically significant at this stage, so everything's still going in. And as we're stacking it, it's a bit like, building a house of cards. Median income has found a way in. That does happen when you're stacking these things in there because the order in which you put them in affects things. And this is showing me the variables that haven't been added in at each point. This is a little table showing me the excluded variables. So if I go down to the fifth table here, we can see median income in thousands did not get added in. That's interesting. So median income in thousands didn't get added in. But percentage county residents with government provided health coverage also didn't get added in. Why did median income in thousands get added in? Because we already got it in there. It's actually in its original form. In fact, if I just chucked out median income, and left median income in thousands in, it'd be a cleaner model, wouldn't it? And because we don't want to put the same variable in twice, effectively. And we can see that the variable that is excluded is percent of county residents of government provided health coverage. The rest all go in. Excuse me, they're all statistically significant. And this is a multiple linear regression model. Now, when we do this, there's something called collinearity. Collinearity is a measure of how much unique variation each variable has at each point as we're putting in. So that's a little number here. And basically, if you've got two variables which are very, very, which are very, which are so highly correlated to each other that they're effectively collinear, then what you'll end up with is a collinearity value which is really, really small because it's a measure of how much unique variance it's bringing to the model. And that unique variance is something which is important because you don't want to be adding in, as we did here earlier on, median income in thousands and median income because they're basically measuring the same thing. And when we looked earlier on, we could see that its collinearity value was in fact zero. So that's because it's bringing nothing new to it. It's already in there in another form. And the rule of thumb is anything above zero point 0.1, generally speaking. But, if you have two highly correlated variables, you're effectively measuring the same thing. What can you do? You can take the ratio of one to another. You can take the average of both of them. They're measured in the same units or something like that. There's different ways in which you might want to combine them together if you want to use them, or just choose one over the other if they're measuring the same thing. I can also ask it to save the actual predictions for me, so I can see the predictions here, unstandardized predictions. If I click OK on that and run that, it's going to save the predictions as extra variables as an extra variable in the model. I know what the correlation is going to be when I compare the correlation of that saved variable against the original dependent variable. It's going to come out as 0.547 because that's the R score. That's the R value. That's the correlation of the fifth model, and the fifth model was used to create this prediction, which is the mortality rate. So I'm going to change that down to just get rid of the decimal places. And if I do some charts here, I'll just do a chart builder here, and we'll just move this mean per capita mortality and put it against predicted mean per capita mortality. Click OK at that point. And there's a relationship between the two. Now there are other assumptions with linear regression that you don't have something called heteroskedasticity, which means that you shouldn't get a funneled relationship. It doesn't mean that your model's invalid. It just means that you should bear in mind that if you get a sort of funneled relationship, it means that the model's less accurate at the higher end than it is at the lower end, and that does happen. It can happen with extremes. It's not too bad here. But if I put a line through that, you get your linear regression equation out effectively for just this predictive variable, this predicted outcome, and the original variable. And you could do the correlation would be around about 0.5. You can also save your model and apply it to a new data set. So you can click on like save here and save it as a new model here. So I could say I'm just going to save this out and say just very quickly. Yeah, I'll just say cancer prediction. cancer mortality rate, got .xml, just saying like that. I'm going to say hit save at that point and click continue and then click OK. It does the same thing again as before, but it's actually created this model. If we come along here and we say, okay, let's just delete this variable here, just delete it. And we'll imagine that this is a new country, that we're trying to apply this model to a new country. It's also split into counties. Or maybe it's a different point in time because, we want to see if the model, we want to assume the model still predicts the outcome well. We could apply that model to a new data set by going to utilities and going to scoring wizard. There's cancer mortality rate. It's found it already because it's pointing to that. Here's the variable it's going to use. I just want the predicted value to come out the back of that, hit finish, and it applies that model to it, showing me the predicted outcome. So that's how we can import a model. Okay, that's linear regression. What have we got? We've got 15 minutes left. So that gives us enough time to just talk about logistic regression. It's much easier to understand logistic regression if you've already seen linear regression because the output is kind of similar. You're going to get a table of, you're going to get fit statistics, you're going to get ANOVA tables, you're going to get a coefficient table that show you some coefficients and even and even things like a beta value to tell you how strongly related each individual variable is to the outcome. But here it is more difficult. It is more abstract. It's abstract because here we're not trying to predict a continuous outcome. We're trying to predict a category outcome. We're trying to predict whether or not somebody is readmitted to hospital within 30 days. We're trying to predict whether or not somebody has sepsis. We're trying to predict the likelihood of no-shows at an appointment. We're trying to predict the probability of a relapse or a staff retention likelihood, whether or not based on whether or not somebody remains, or odds ratios you could use. Sometimes it's used to create, it creates odds ratios in case control studies. It actually creates these. And it helps you model the effects of comorbidities on procedure outcomes. And that's because the outcomes aren't continuous values. So, and if they're not continuous values, standard linear regression won't work. Standard linear regression doesn't understand the idea that there's just a two-category outcome. So when the outcome consists of two categories, we use binary, and when the outcome consists of three or more categories, we use multinomial logistic regression. And logistic regression gets around the limitations of describing relationships of straight lines when you're trying to predict just a two-category outcome, because it uses a non-linear approach to it. It uses what's called a sigmoid curve. And the sigmoid curve looks like this, and the sigmoid curve relates to probability and some sort of stimulus, some sort of variable. So if you just imagine I've got a website or a web store set up and I'm selling iPhones, if I'm offering zero discount on the iPhones, I may not sell any. The probability of responding to it is pretty much zero. Why would you buy from me? Why wouldn't you just buy directly from Apple or something like that? But as I increase the discount, the probability of people responding to it, starts to increase. And this line relates to that. This curvy linear line. It's kind of an inflection point where you split from being 50% chance to 100% chance. If I offer you a 100% discount, 100% chance, why wouldn't you take that? Probability of responding. So in the same sense, if we want to look at the probability of relapsing on the treatment, we've got some sort of health condition measured by BMI or cholesterol, something like that. The probability of relapse might increase dependent upon that value. So this is exactly how logistic regression works. So the question is what are these numbers on this x-axis? Because what happens is there's a special formula that converts the values of predictor coefficients, the coefficients that we get out in the tables, like the y equals mx plus c, and they turn them into probabilities. And these numbers that you get on the x-axis, these are the coefficients that the model kicks out. Now, it so happens to be that this formula is called a link function. It's just basically its job is to convert these numbers into probabilities. And the formula happens to be 1 over 1 plus e to the power of minus z, which you're probably not going to remember, but it's actually regarded as a fairly simple link function, and it just converts the output, the numbers from a logistic regression and other types of regression, into something meaningful, which is probability. But the downside is that the numbers themselves aren't going to be meaningful until you convert them into probabilities, really. So the numbers themselves are highly abstracted, as we'll see in a moment. So we're going to use logistic regression to model low birth weight. So let's open up a data set. First of all, I'm just going to get rid of that output. Don't want that anymore. Open up a data set here, which relates to low birth weight. Birthweight.sav. So this is a well-known, famous data set. How many records have we got? Um, 378. Okay. I'll just sort by ID here. Save that. So, and we've got the actual birth weight here in grams. So we can see low birth weight. If I just did a little chart here, I'll just do a little table here and say, okay, I'll just do means, table of means. So compare means, compare means. Let's see, compare means and means. So we'll say, what's low birth weight by birth weight? I just want to find out what the thresholds are. So I'll say, what's the minimum and the maximum value, maximum and minimum. There we go. I don't want the sum. Click continue and okay. So yeah, as soon as you're above 2523, which I guess is grams. Sorry, as soon as you're above yeah, 20 about I guess 2500, that's what it would be. You're in the healthy normal birth weight group. That's what it is. And if you're less than 2500, you're in the low birth weight group. So that's what the babies are measured in. I don't need this. I'm just going to delete it because I don't need it now for at the moment. What I want to do is predict this outcome. I'm going to go to analyze down to regression and down to binary logistic because it's a two category outcome. And I'm going to put low birth weight in. And I'm going to put one variable in here, which is weight of mother at last menstrual cycle. That's called LWT. I'm going to click OK on that and just run the analysis, and you'll see the result. And then we'll add in other variables as we did previously. So the first thing it does is it gives me what's called a classification table. That's like a crosstab. It's predictions against the observed. And basically, this classification table at this point simply predicts everybody to be normal birth weight. That's all it does. It just predicts everybody to be normal birth weight. Why does it do that? Because that's what you're trying to do better than. There's a majority of cases are normal birth weight, so 68.8%, nearly 69% of the cases are normal birth weight. So you might as well just predict everybody to be normal birth weight, all the babies to be normal birth weight, and therefore you'd be nearly 69% accurate. So you're trying to do better than that. So that's kind of your beginning block zero, as it calls it, or block zero. It's what you're trying to do better on. You're trying to beat that and try to get a better prediction out. Now, to be fair, it's quite arbitrary. I don't like these types of classification tables because in order to be predicted to be a low birth weight, you'd have to find a case which had a more than 50% chance of being low birth weight. And at the moment, the average chance of you being low birth weight is what, 39%? About 30, sorry, 40, was it 41%? Something like that. If I round that up to 69%, oh, 31%, sorry, 31%. Yeah, so I round up 69%, 31. So, you have to find a case where, they had a greater than 50% chance for them to go into that cell. That doesn't mean the model's not any good. It just means that, you haven't got many cases where people are very, a high percentage chance, where the cutoff value is 0.5, 50%. So then it shows me variables in the equation, and it just shows me the constant. And the first thing we see here is the constant. And the constant here is actually not a b value, which relates to the uh, the normal weight itself. It's actually the log of the odds of that value here, 68. That's really weird. So it doesn't even show you the value in odds. It shows you the value in the log of the odds. Why does it do that? Because that's the formula that converts the number into something meaningful. And guess what? If I multiply, if I put that through my formula, that is equal to minus z. If I multiply it by minus, if I minus it, it makes it a positive number. That would be 1 over 1 plus e, which is a value called the exponent, which is a bit like pi. If I raised e to that number and I added 1 on and divided it by 1, it would give me a value of 0.31, which would be about 31%. Yeah, 31% which would say that's the percentage chance of you just using the constant of you being in the low birth weight. And it's saying, yeah, it's statistically significant because it's better than random. You know, it's better than random. Um, at this stage now, we now have the possibility to enter the variable weight of mother at last menstrual cycle in pounds. We can see that this is significant. And it begins by adding that in. It's telling it it's significant at that step, at that block, and that model. Well, they all go in the same step, in the same block, and in the same model. You can actually split the steps up and the entry of variables in different steps and different blocks. But here it's all the same value. It's saying, yeah, it's significant. It actually tries to give you something what we call pseudo R-square values. They tend to be really, really small, but suffice to say, the larger the value, you know, the more significant or the greater explanatory power, the more correlated that variable is with the outcome, and they're pretty weak here. The value that most statisticians use is called -2 log likelihood. This is just a number. It's not something you interpret directly, but the smaller that number is, the less error there is in the model. So as you build a model and you add in more variables, you see the -2 log likelihood going down. And in fact, if you wanted to compare one model to another, you would usually use the -2 log likelihood value. It's just an abstract number, but the smaller it is, the more accurate the model is, the better the fit is. And here it says, okay, I've added in the variable. It hasn't changed the classification table because nobody, even with this active variable here, no case has a percentage chance of greater than 50% of being low birth weight. So it doesn't change the table, but it does change the model. And it adds it in. It says, there you have this value. This is a minus number saying that the heavier the mother, the less likely they are to be in the low birth weight group. So it's a negative value. And again, if I took these coefficients and I multiplied weight of mother by last menstrual period by 0.013, and I added on 0.837 onto the end of that, that's going to give me a number. And I would then put that through my special link function, and for every case, it would give me a probability value of them being a low birth weight. Interestingly, the constant at this stage has become non-significant, and the constant at this stage non-significant. It just means that it's not it's pretty weak. You could get away with not actually including it in the model at all at this stage. The exponentiated b is this value. It's been raised to the power. E has been raised to the power of it, and it actually shows that anything under one means it's having a negative effect, and anything over one is having a positive effect, and it actually relates to the odds. So let me add in another variable here. Let me choose a different variable here. I'll show you odds. Here's smoking status. I can throw this in. I can treat this as if it's a numeric variable because it only has two values, one and yes. So I click OK at that point. The smoking status goes in, and it has the exponentiated b of 2. What that means is that the odds of being of having a low weight baby are doubled. They are twice as high if you're a smoker than not. If it was zero point 0.5, it would mean you're half as likely. The odds have been halved. So this is a really good way for us to see the effect and measure the effect of variables in terms of which ones have a greatest effect. But they are affected by the units. Here we only have a change from 0 to 1, and it doubles it. Whereas previously, you know, if I put in weight of mother, the exponentiated b is much smaller because, of course, it's each weight in pounds reduces means that the odds are 0.988. So rather than 1, if the odds were equal to 1, they'd be exactly the same. So it's only reducing it a little bit, but that's because it's measured in pounds, and it could be 180 pounds, something like that. So it's affected by the model. So I could just continue this process here, and I could add in these other variables here, like history, hypertension, and these other variables, and put in age of mother, and do what I did last time. I put smoking status in. I could say, okay, let's use forward LR, forward conditional, and it builds a model for me. It builds a model for me step by step. Here we have the model. It's being built, and each time you see the -2 log likelihoods going down, and the R square values, these pseudo R square values, are going up. The percentage table now is starting to find a few, the classification table is starting to find a few people, just a few cases where the probability is greater than 5. Sorry, greater than 0.5, 50%. I don't really pay much attention to that. But I would look at step 5 here and see which of these are statistically significant. They're all statistically significant. They're all contributing to it. And we can see that history of premature labor. Oh, look at that. History of hypertension has a value of 6. If you've got history of hypertension, then the probability of, the odds, sorry, not probability, the odds increase by a factor of 6. You're 6 times as likely to have a low weight baby. And lastly, just to finish up here, I'm going to add in the variable race. Well, the variable race isn't a binary variable. It's actually white, black, and otter. And this is called a factor field. And we have to tell it that it's a factor field. We go to race here. And what we do is it does a special type of internal coding. By default, it will choose the first category. The first category is white here. And it will show the effect of not being white for the other two categories on the odds of being having a low birth weight baby. So when we look down here, we see at the bottom here, we look at this last variable here. It says step 6 was a model of terms. There's race. You can see race has no coefficient, but it's significant overall. That means the bear. Race 1 refers to African Americans or black people, and race 2 refers to those in the other group. And what that's saying is the effect of being an African American versus a white person, because that's your reference group, the white person people, means that the odds increase by 3.6, and the effect of being in the other ethnic groups versus a white person increase the odds by 2.53. In this occasion, again, we can save our model out. We can ask it to save the probabilities and the group membership. Here, instead of the linear regression where we're getting a number coming out, like this is the mortality rate, it's saving us as a probability. So I'll just reduce the decimal places here down to 2, and it's saying that 29% chance of being low birth weight, 45% chance of being low birth weight. That's why they're all being predicted to be normal birth weight. The only times anyone's predicted to be low birth weight is if the probability is greater than 0.75. Well, you might actually decide that anybody with a value greater than zero point 0.4 is quite risky, and that's how you set your cutoff at that point. It's effectively a measure of risk at that stage, so it helps us measure the risk. Okay, that's the end of that particular example, and we can now, just before we go, point out again there are a lot of regression methods that you can use. And there are additional resources that these will take you to links or video links of additional resources that you might want to check out. And we do have a portfolio of online training materials which are free to our customers and available for purchase. And as I said in the last session, we actually have our own chat SPSS AI chatbot these days, which we've developed ourselves. We made it freely available to people in any use of SPSS, which might be really useful if you want to try and understand what's happening. And we have a lot of experience in delivering services, helping people buy software. We provide SPSS online software. You can convert your IBM software licenses to us, and we'll look after them for you because we're experts in that area. We provide guided consultancy and training to help you develop your own in-house skills. And we generally offer no strings attached technical and business advice related to all analytical activities, as well as formal technical support services. I do hope you find that useful. In our next session, we're going to be looking at applying SPSS to marketing procedures and marketing applications. In the meantime, we look forward to you logging in again in the near future. Thanks very much.